Good morning, students. Today we are going to continue the remaining portion of the chapter Chemistry of Carbohydrates with the heading 3 representations of glucose structure. Glucose structure is represented mainly by three forms. That three forms we are going to see now. Before that, first we need to understand about the hemiacetal form of glucose. Hemiacetal form. That form is proposed by Emil Fischer in 1883, and for proposing that structure he awarded Nobel Prize. What about that form of glucose? This is the structure, typical structure of glucose. In this structure, the first carbon, it is condensing with a OH group of fifth carbon to form a rectangular form. That form is called hemiacetal form. It was proposed by Emil Fischer. In this way, a box like rectangle like structure is forming out of this through process of condensation. Condensation means that bond is formed by elimination of one molecule of water. Then in biological system, usually the glucose exists only in pyranose form. Pyranose form means it is a perfect ring with 6 carbon. In this form, most of the glucose exists in biological system rather than the rectangle form proposed by Fischer. And this pyranose form is proposed by Sir Walter Howard in 1925. Okay. Then these two are pyranose form. 6 carbon perfect ring. And this is the beta form and this is the alpha form. And regarding the proportion, these three are the representative structure of glucose in biological system. And this beta form occupies 63 percentage in biological system. Alpha form occupies 36 percentage. This same time, furanose form, that is the pentose form, form only 1 percentage. That includes both alpha form and beta form. Together, the alpha and beta form of furanose constitute only 1 percentage of glucose in the biological system. Then fructose is a ketohexose that we are going to see now. Fructose is a ketohexose. Ketose. That means there that functional group is a keto group instead of a CHO group, aldehyde group. Okay. That keto group is attached to the second carbon. So, here the second carbon is the anomeric carbon. Okay. This is the structure of fructose. Then we are going to think about how many isomers are possible out of the structure of fructose. Yes, 8 isomers are possible. Why? Because here 3 asymmetric carbons are present. So, 2 raised to 3 is equal to 8 isomers. Okay. Then we are going to find which are the 3 asymmetric carbon in the structure of fructose. Let's see that. Consider this carbon, this bond and this bond same. So, it's not an asymmetric carbon. Then consider the second one. Here carbon bond. Here one oxygen, again one oxygen. Same. So, it's not asymmetric. And next carbon. Here this is the group present attached to this bond. and to this bond OH, to this bond H, and to this bond this different. So it is an asymmetric carbon. Number one. Number two, here to this bond, this group is attached, and to here it is H, here it is OH, and here this is the group. So this is also an asymmetric, second asymmetric carbon. And next one here, this is the group attached to this bond. This is H, another different. This is another different, and this is another different. Again, the third asymmetric carbon. Then come to the last one. Last one here. This is the group. Here H, again H. So it is not an asymmetric carbon. Only 3 carbons are asymmetric here. So 2 raised to 3 is equal to 8 isomers are possible out of fructose. And in the case of fructose, D-fructose is seen in biological system. D-fructose means levorotatory, rotating towards right hand side. That type fructose only is found in biological system, and it is a major constituent of honey. Then we are going to another important section, that is reactions of monosaccharides. Mainly 3 reactions are important properties of sugar. They are mutarotation, reducing property, and formation of osazole with phenyl hydrazine. Mutarotation we already learned in the last class. It is the change in rotation with time. And that change is there as that plain polarized light pass through different isomers. So that property first we are going to see, it is something connected with the formation of an enediol. And connecting with that, we need to understand a chemical process phenomena called tautomerization. Tautomerization, I think you have already learned in your chemistry during your PG class. Anyway, I am once more explaining what is tautomerism. Tautomerism means a single chemical compound. It exists in a intermediate form. It is the enedial form. That enedial form is interconvertible to another isomer of this chemical compound by the transfer of protons. This is the process that helps in the interconversion of the first compound to its another isomer. That phenomena, that change of the first chemical bond to its isomer through formation of an interconvertible intermediate compound, that is NADL. That process is called tautomerism. And that NADL we can call it as tautomers. And it is a structural isomer of the original chemical compound. And also that tautomer is interconvertible. Okay. And that reaction commonly results in relocation of protons. Next, we are by relocating, by changing the position of proton, that tautomers are forming. So we are going to see the process, how from a glucose, how a fructose is forming through the process of forming an NADO form. Okay. This is the glucose. It's an aldoses because aldehyde group is present here, CHO group. And next, this bond is breaking. One of this bond is breaking, and we know that 2 protons or electrons are here for forming one covalent bond. So in this way, 2 electrons are free now. And here also this bond also dissolving. So again here 2 free electrons. Then what is happening? Using these two electrons, another double bond is forming here. Yes. Then what? How many electrons still free here? Here one electron and here. That together again combine and form an OH group here. And then for O, a double bond is necessary to attain its valency, stable valency. So it is negative here. And this form is the NADL form, is the intermediate stage. It's not stable. It can be interconvertible to another isomer of glucose. Next, we are going to see how that isomer is forming from NADO. This is the NADO form. Once more, I am going to rewrite the structure of NADO. This is the NADO. And what is happening again? This bond is dissolving and two electrons are freed, and using these electrons, a double bond is forming here. Okay, then 1, 2, 3, 4, all the bonds satisfied. And also here, this H, the bond between O and H, that is dissolving, and that H is moving and joined with this functional group. Okay, in that form, in that way, CH2OH is forming here, and that structure constitutes fructose. So this is the tautomerization process. An isomer of glucose is forming through formation of an intermediate, that is the enediol. What is the condition for causing this tautomerization? The tautomerization happens in mild alkaline solutions. That solution should be mild alkaline. Then only this tautomerization happen, results in the interconversion of one glucose to its isomeric form. And that interconversion of sugars through an NADL form, that process, that interconversion is called Lobride-Bruin-Van-Ekenstein transformation. Okay, what is that? Lobride-Bruin-Van-Ekenstein transformation. What is that? It is the process of interconversion of sugar. Sugar is interconverting to its isomer through an NADL form. Yes, that transformation. And regarding the reducing property, sugars with a free aldehyde or ketone group are powerful reducing agents in alkaline medium. What is a reducing agent? Reducing agent means it can give hydrogen or proton. It's a donor, and it underwent oxidation. Correct? Okay. At the same time, what is an oxidizing agent? Oxidizing agent means it takes hydrogen or proton and give oxygen. So it's an acceptor of proton. So oxidizing agent underwent reduction, right? Okay, that things we need to keep in our mind while reading this. Suppose there is an alkaline medium, sugar is present, and it is having free aldehyde or keto group, then it is a reducing agent. That means it is ready to donate proton. And in that condition, an oxidizing agent also present in that medium, like cupric ion. Then what will happen? That cupric ion certainly will receive or take that proton from the sugar and oxidize that sugar. Oxidize means it add or give oxygens to that sugar and help to form carboxylic acids from that sugar by breaking its double bonds. So it's very clear that sugars means sugars with a free aldehyde or ketose group can act as reducing agent in alkaline medium. Okay. And these are some examples of carboxylic acid that formed from glucose by the addition of oxygen. All have. And regarding these structures, also some other point also coming that I will tell you in the coming slide. Next. Benedict's reaction, Benedict's solution, Benedict reaction is familiar for you in your UG classes because in UG you have done a practical using this Benedict reaction for urine analysis to understand or detect the presence of glucose, right? Okay. Then Benedict solution means it is used to detect the presence of sugar in urine, to detect diabetes mellitus. And what's the inference at that time you noted during that practical time? The end product, end result is a red color. Okay. Then what is the reason for the red color? That's the thing. Because first we need to understand what the composition of Benedict solution. Benedict solution contains sodium carbonate. Look, sodium carbonate, copper sulfate and sodium citrate. Suppose this is an alkaline medium. Okay. And this medium contains sugar in it with having a free aldehyde or keto group. And this sugar, as it is present in alkaline medium, it converted to undergoes tautomerization to form the tautomer, that is the enediol. Okay. Then along with that, in the medium present copper sulfate. From copper sulfate, cupric ions are available form, and this cupric ion oxidize the enediol and form cuprous oxide is red color. Because of this reason, uh, as we test for the presence of sugar in urine, we got a red color as the inference at its endpoint. Okay, that's a Benedict's reaction. Um, and one more thing, this Benedict reaction, that reaction to give a red color, that is not specific to glucose only. That reaction can give by any sugar with a free aldehyde or keto. Okay, so it's a underlined chemical property of sugar. Then osazone. What is osazone? Osazone, they are derivatives of carbohydrate. It's a compound derived from carbohydrate. And which sugars form osazone? All reducing sugars can form osazone. These are the images of osazone. Some needle-like structures are forming out of the carbohydrates. And on what condition these oxozones are forming? When this carbohydrates it is treated with this compound's name you need to learn, phenylhydrazine. It is treated with the phenylhydrazine at boiling temperature. Then what form? Oxazone is forming. And the oxazones are typical. Each type of sugar have its own oxazone. These are the pictures of different oxazones for different sugars. But for glucose, fructose, mannose, the oxazone form is same. It's a needle-shaped crystal shown here. The same type of oxazone is forming for glucose, fructose, mannose. Why is it so? Because all these things, all these glucose, fructose and mannose, they differ with respect to first and second carbon. And that difference is masked during the formation of this oxazone. That's why all the oxazones form out of these three isomers resemble in a same way, similar appearance. They because of that reason, all the oxazones formed out of glucose, fructose, and mannose appear similar. What's the application of this oxazone? Because each and every sugar have its own oxazone. So, if we want to analyze which sugar is present in a urine sample, we only need to let that urine to react with the phenyl hydrazine at boiling temperature, and then check what type of oxazone is formed. Rarely itself very clear each and every type of oxazone particular to each type of sugar. In that way we can differentiate. Understand? Okay. Oxidation of sugars. Under mild oxidation condition, that is in the presence of hypobromous acid, what is happening? The aldehyde group is oxidized to a carboxyl group. The aldehyde group means we know that it is attached to first carbon, and it is oxidized. Oxidized means one more oxygen is adding and forming a aldonic acid. This is aldonic acid. Example for aldonic acid. Here we can see that COOH, a carboxylic acid form. So, under mild oxidation condition, this is the reaction happening. Out of glucose, which type acid is forming? Gluconic acid. Out of mannose, mannonic acid. Out of galactose, galactonic acid is forming. When that aldehyde group is protected, then what will happen? Then that oxidation happen to the last carbon. Yeah, here we can see that oxidation. So here that carboxyl group is forming to the last carbon. And from the glucose, because of such type of reaction in which aldehyde group is protected, which acid is forming? Glucuronic acid. From mannose, mannuronic acid. From galactose, galacturonic acid is forming. Then under strong oxidation condition, because in the presence of strong oxidizing agent like nitric acid and high temperature heat, then what will happen? Then it oxidizes both ends, first carbon and the last carbon. So 2COOH, dicarboxylic acid is forming there. COOH, COOH. So here from glucose, as a result of such type of reaction, glucose saccharic acid is forming. Mannose, mannaric acid, and from galactose, mucic acid is forming. Say typical name, a special name. Then structure is given here. What is the application? This mucic acid, it can form insoluble crystals. So, by detecting that, we can use this principle to detect the presence of galactose in a given sample, because galactose is present out of it. If nitric acid and heat is given, then mucic acid will form. Then we can infer that it contains mucic acid. Then furfural derivatives. How furfural derivatives are formed from carbohydrates? How it is forming? The monosaccharides reacts with the concentrated sulfuric acid. And as a result of that, 3 water molecules are eliminated. And by eliminating 3 molecules of water, a hydroxymethyl furfural is forming if that monosaccharide is a hexose. And at the same time, only a furfural, R is missed here. Only a furfural is forming if that monosaccharide is a pentose. Whatever be the result, it again continuously undergoes condensation with the phenolic compound and may result, and they gave the result, there are colored products. Colored products are formed. In this way, furfural derivatives are forming from carbohydrates. With this, we finish today's section. Thank you.